Okay, I'm going to also introduce an idea called inclined planes. Now, inclined planes it basically involves, like it's described as, an incline with a mass on it at some angle theta. Okay, the challenging thing here is to identify the forces here and to look at this because the axes have kind of switched in terms of horizontal and vertical. Now we're at some angle. Well, to deal with this, let's first label some of the forces we already know. We know here that there's going to be a force of gravity. Um, Here's a force of gravity here pulling down on this. Okay, I'm going to call that, there's your force of gravity pulling down. There's also a force normal pushing off in this direction. Okay, so there's a force normal and a force of gravity. I'm going to ignore friction for now and just label these two forces and try to look at this. Well, to identify this a little more, let's take a look at some of the angles and to break this up. What I want to do instead is instead of having my XY axis, okay, instead of having it like this, instead of having it, here's Y and here's X, okay, instead of having this, what I want to do is take that whole axis and tilt it. So in other words, now this will be my X and this is my Y. I have different notation instead of X and Y, and what I call them is I call them parallel to the ramp and perpendicular. So parallel would be X, perpendicular would be Y. Well, in order to define this perpendicular, let's take a look here and think, well, Y is, if force normal is pushing up this way, okay, and this thing, let's say, is not falling, it's not accelerating in the perpendicular direction, okay, in the new y direction, that must mean that there's a component here acting this way. So in other words, if f ends this way, there's a component acting this way. Well, it turns out that we can take gravity and break it up into components because now, if you look at it, it's now at an angle. I'm just going to tilt this whole axis this way so it's horizontal. Just so you can see here, if this is horizontal, gravity is actually at an angle. And it turns out that this angle will also be equal to theta. I'm going to save some time here in terms of how to figure that out. But just so you can see, if this is theta, I'll just show you very quickly. This is going to be a 90-degree angle right here. Okay, here's a right triangle. So that's theta. This will be the complement of that angle. Okay, in other words, 90 minus theta. Well, if you look here, there's also a right angle right here. This is a right angle. And so if this is a right angle, this would be the complement of this angle. And so this theta has to be the same as that theta. They have to be identical. Now, I'm going to just bring this back here and say, well, if that's theta, okay, and Fg is equal to mg, that means that this one right here would be equal to mg times the cos of theta. This side, this component here, would be mg times the sine of theta. Okay, I'm going to call this one F perpendicular. I've write a little upside down T to represent perpendicular, and this one I'll call F parallel. I try to stay away from X's and Y's. You could use that, but I'm going to call it F parallel to meaning the parallel component of gravity. This is the perpendicular component of gravity. Of course, this is what gravity is actually doing, the hypotenuse right here. Okay, why are these useful? Well, I'm just going to write them a little larger here and say that F parallel is equal to mg times the cos of theta, and F parallel is mg times the sine of theta. These are very useful in solving problems, and I'm just going to give you an example here to solve. So if I had another inclined plane here, I'll just draw a quick inclined plane. Alright, there's a mass here. Okay, I'm going to give this thing friction. I'm just going to say there's a mu here that's not equal to 0, some value mu. Okay. If I want to know, let's say this thing, I just drop it on here and I'm going to know how much it's going to accelerate. Okay, well let's take a look at what we know here. We know that there's a force of gravity. Okay, we know that there's a force normal. And if this thing's trying to accelerate, let's say down, we know that there's going to be a force of friction opposing it. Okay, I'm just going to make a general force of friction right here going up. So this thing's going to try to accelerate down. To balance all these out, okay, you're going to get here that's force normal, force of friction, force of gravity. Well, it turns out here that we have to break this up into components, and we know that in the parallel component, Okay, I know that there's going to be a force parallel pulling down. Normally I had it down here. I can just move it up to my free body diagram and just make it force parallel here. Here is going to be a force perpendicular. What I know, if this is actually standing still, in other words it's not moving anymore, I know here that force parallel must be equal in magnitude to force of friction, because the net force in this direction will be 0. We also know here that force perpendicular must be equal to force normal. This helps me solve problems because if I know this, that means force normal must be equal to mg cos theta. Also, I know that force of friction, which will be equal to mu Fn, will be equal to mg sine theta. And we can start equating things here. Fn we know is equal to mg cos theta. And you get some interesting results here, where mu Fn and mg sine theta and mg cos theta. Okay, if I move this one, I'm just going to bring this down here, and instead I'm going to write mu mg cos theta. If this force of friction, okay, is equal to my force parallel, which equals mg sine theta, you get something interesting that happens here. Just to show you this scenario here, the m's will cancel, the g's will cancel in fact, and what you'll get is you'll get mu is equal to sine of theta over cos of theta, when in fact sine over cos is actually equal to tan of theta. You can play around with this all day, but inclined planes are very useful in terms of solving things. Okay. And you can solve for other variables. Sometimes force parallel will beat force of friction and it'll accelerate down. Sometimes force of friction will actually be greater, in which case it'll slow down if it's already falling down the incline. But it'll take some practice and you'll get used to solving problems using inclined planes.